Hello students, I welcome you all in today's video. In today's video, we are going to talk about the motion of a charged particle in uniform magnetic field, right? So I'm just talking about one case here when the charged particle is moving in magnetic field and angle between the velocity of the particle and magnetic field is 90 degree. That means the particle is moving perpendicular to the velocity, okay? So let me just tell you one point. Suppose if you have the magnetic field like this towards right, okay, and there's a charged particle going to enter in magnetic field like this, right? Then what is going to be the direction of force acting on it, right? So to get the force, we know that we have to use right hand thumb rule, because the force that we have, magnetic force, is nothing but this is q times v vector cross b vector. So we have to go towards v cross b, okay? So this charged particle is q and having velocity v. Now v is like up and your field is towards right, so I have to curl my finger towards right. That means my thumb is inward, okay? So if you talk about the force here, the force is perpendicular to velocity. In this particular case, the force is basically inward, right? That means force is perpendicular to velocity, okay? Then what kind of path we can expect? See, we have seen in the circular motion that whenever the force is perpendicular to velocity, that force behaves like centripetal force. And whenever centripetal force is there, we have circular path. So whenever force is perpendicular to velocity, because of that particular force, the path has to be circular. So whenever a charged particle is going to enter in a magnetic field perpendicularly, the path has to be circular. So let us take one example here and see what is happening. Here I have taken a dot magnetic field. That means the magnetic field is out of the plane like this, okay? Consider this charged particle having charge q and velocity v, which is moving like this, okay? So if you talk about the force is going to be v which is towards left, and the b is up. So the force has to be towards like this, towards up in this particular diagram. So the force we have is perpendicular to velocity. Not only this point, if you check the second point also, the velocity is going to be like this, right? So velocity is this, and if you curl the finger up towards field, the thumb is giving you the direction of what? Force. So your force is towards the center of the circular path. So basically in this part, what is happening? Whenever the charged particle is moving like this, when the velocity is perpendicular to magnetic field, the magnetic force behaves like a centripetal force, okay? And the path is going to be circular. If you talk about the magnetic force here, that is qvb sine theta, its magnitude is qvb sine theta, direction we can see easily. And if you talk about the theta, which is the angle between v and b, that is 90 degree in all particular cases. So if you talk about the sine 90 value, that is 1. So your force value is just going to be qvb, right? So if this is the force, this is going to behave like what? Centripetal force, okay? Now we know that centripetal force is nothing but mv square by r. So we can basically get the radius of the circle. What is going to be the radius of this particular circle, we can get from here. What I'm going to tell you, this is qvb, that is centripetal force, and that is mass times centripetal acceleration, which is v square by r, okay? So here v and v get cancelled out, and the radius that we got is mv by qb. That means if the particle is going to complete the circle, the radius of the circle is just mv by qb. One thing we can understand here, that the radius is perpendicular, the radius is basically proportional to velocity. You increase the velocity, the radius of the charged particle, means radius of the circular track, will increase, okay? Now since we have the radius, so we can also find out that how much time it is taking to complete a circle, that is time period. So the time period is going to be 2 pi times r, that is the circumference length, by velocity with which the particle is moving. Speed is the better word here, because the velocity is changing its direction everywhere. So the speed is v with which the particle is moving. The time is going to be 2 pi times r, which is mv by qb by v. This get cancelled out. So the time is going to be 2 pi times m by qb. Okay. Now you can see here the velocity is getting cancelled out. That means the time period is basically independent to velocity. Okay. That means if you talk about two charged particle having two different velocities, they will take same time to complete a circular track, right? But definitely the charged particle having more velocity, that particle will have bigger radius, but the time taken to complete the circle will remain same. That is 2 pi m by qb if the particle is completing the circle. Why I'm saying if the particle is completing the circle? Because if the particle is completing the circle, only then this time taken is going to be 2 pi m by qb, right? In later cases, we will see that if the particle is not able to complete the circle, suppose in that case, let us say the particle is completing the circle like half circle only, then the time spent by the particle inside magnetic field is going to be just that angle subtended by the path in radian, that times m by qb. So if the half circle is there, so angle is pi, then time is going to be pi times m by qb. Here we have the angle subtended by the path is 2 pi, so we got time period is 2 pi m by qb. Since we have time period, we can basically find out the frequency also, and frequency is just 1 by time period. So that is 2 pi m by qb inverse of this, which means this is qb by 2 pi m. This is the frequency. Okay. So frequency we have is qb by 2 pi m. Okay. Now, one more thing we have to here understand that actually this concept is very, very important to solve the question which they will ask you based on this concept, that the radius is basically always uh, pointed towards the force, or we can say the center of the circle will always lie on the line of force. You can see here, if you just extend the line of forces, it has to pass to the center only, right? So if I will give you a case, let us say the magnetic field is cross on like uh, right side to this point, and if I will tell you that the charge particle is entering here like this, then if I will ask you to draw the path, so to draw the path we need what? We need the center of the circle. So V cross B is like this. So this is the line of force. On that line of force only we have the center of the circle. We can just draw the path like this. Okay. So till this point it is going to be a circle, and here the particle is again coming out. In this particular case, if you talk about the time spent is going to be pi radian times m by qb. That means the angle subtended by the path in radian, that times m by qb is the time spent by particle in magnetic field, right? So I hope this is clear to you guys. Thank you.